So here's a pulley problem. We have 3 pulleys. We have 2 ropes sort of connecting them and the various masses, and the ropes are inextensible. And the question is as follows: find the velocity of B given velocity of A is 2 meters per second upward. Similarly, find acceleration of A given acceleration of B is 3 meters per second square downward. Okay, so those are the questions. Now, how does one solve this problem? This is an example of constrained motion. Constrained motion meaning these masses are constrained to move in a particular manner by virtue of the fact that they're connected by these pulleys and these inextensible ropes. Okay, so all ropes are inextensible, by which we mean length is a constant. They do not change length. Okay, so that's the basic principle. So what we need to do let's use a different color perhaps. Find relationships between VA and VB, and similarly AA and AB. Okay, velocities of A and B and accelerations of A and B. Well, I guess these are different sort of problems, so to speak, right? So what we mean by that is find relation between VA and VB and find another relationship between AA and AB is the problem. Okay, so if we can find such a relationship, then we are all set. So let's go about doing that. Solution. The first step is to, if you're given a picture like this, to try to see if you can either mark up this picture itself, or if the picture is a bit cramped, you might want to redraw the picture a bit bigger. Okay, let me actually redraw the picture a bit bigger here. So this is a big pulley. This is A. Another big pulley goes all the way to the ceiling. And you have a bigger pulley perhaps, goes all the way to the ceiling. The radius of these pulleys don't matter for these problems, it turns out, so I'm just drawing them however is convenient to draw them. Okay, so in this picture I had kind of drawn the ropes connecting the pulleys in different colors to indicate that there's a green rope here and then there's a blue rope here. So let me actually use those colors again. Kind of like so. And then a green rope. For that, okay. Now let's actually define various quantities. Okay, the first thing to do, let me say step 1. The first thing to do is define variables for positions of key masses, in this case A and B, if there are more masses, you want to write them down. And then, so let me actually do that first. So I'm going to define the position of mass A, let's say, starting from this point, okay? So I'm going to define this to be y sub A, okay? I'm going to define this to be y sub A. And if you sort of extend this thing, we can define maybe this to be y sub B. Now, you might ask, like, why did we not go from here all the way to the mass B? Okay, why did we not extend this arrow all the way until here, for instance, like so? Okay, so we could have defined this whole thing as YB, but we did not do that. But we can certainly do that as well. Okay, so that is a perfectly fine thing to do. The difference between going from here to here and going from here to all the way here is basically this length. Okay, this length, this is just another piece of rope. Because all the ropes are inextensible, this is just some constant. And in these kinds of problems, we will be differentiating these positions anyway. So constants, any constant piece of rope will drop out. So you can, so basically, for instance, if you're tracking the velocity of B, the velocity of B will be the same as the velocity of the midpoint of this pulley because they're connected by this inextensible rope. So that's sort of why we define YB to go from here to here. Like I said, you can certainly do the problem by defining it until here. Similarly, we could define YA and YB all the way from the ceiling if we want, but we happen to do this from here, sort of more convenient. And the distance between the ceiling and this dotted line is a constant because it's the length of this rope. So when we differentiate, these things will drop out. So that's why we define the position of A and the position of B not from the ceiling but from this point. But if you happen to define it from the ceiling, totally fine as well. Things will work out eventually. Okay, so that's the ceiling. So that's step one. Step two is basically the same as step one, which is define variables for other segments of rope as necessary. Okay. So let's do that. Let me actually define this piece of rope. To be Y2, okay? Let me define this piece of rope to be Y1. Let me define this piece of rope as until here, basically, as Y3, okay? Okay, I guess you can already see that Y1 equals Y2, but let's just leave it as such for now. Okay, so what's the next step? Step 3. Step 3 is write down expressions for lengths of various ropes. Okay, so let's do that. Let's first do the blue rope. Okay, and let me draw that in blue rope. Okay, so the length of this rope is going to be YA plus half the circumference of this pulley plus Y1 plus half the circumference of this pulley plus Y2 plus some length here, which is going to be constant because it's the distance from the ceiling to this dotted line. Okay, so this is some constant. It's basically the same as this. Okay, it's the same constant, but that doesn't matter as much. It's some constant. Okay, so the blue rope is basically YA plus pi times R, where R is the radius of this pulley. These pulleys could be the same radius or different radii. It doesn't really matter, but if you want to be careful or precise, you can say R1, R2, R3 for the different pulleys. Anyway, they are going to go away. They are not going to withstand or remain after differentiation because they are going to be constants. Pi R is a constant because the radius is a constant. When you differentiate, it goes away. So in any case, so pi R1 plus Y1 plus pi R2 plus Y2 plus constant. Okay. Plus constant equals total length equals constant. Okay, so we can differentiate. We basically have YA dot plus d by dt of pi R1 is basically 0 because it's a constant, plus Y1 dot plus 0 plus Y2 dot plus 0 equals 0. Okay, so we have YA dot plus Y1 dot plus Y2 dot. If you kind of realize that Y1 equals Y2, then you can just use that here, because Y1 equals Y2, Y1 dot equals, let's call this 1, Y2 dot, let's call this 2, let's plug that into 1. So we have YA dot plus 2 Y1 dot equal to 0. Let's call that 3. Okay, so we've gotten one equation for the blue rope. Let's get an equation for the green rope. Okay, so the green rope length is going to be Y3 plus pi for this pulley, R3 perhaps, and then YB, and some constant. It's actually the same constant, it turns out. So that's sort of recall why we said those constants drop away. So for instance, the constant became 0 because we differentiated it. So green rope, we said Y3, pi R3, YB, constant. Okay. Constant equals total length which is still a constant because it is inextensible. Now, when we say constant, what we technically mean here is not that this constant is the same as this constant, but that this is some constant, this is potentially some other constant. Similarly, this is some constant, this is some other constant. And all that matters is that it's some constant, because when you differentiate it, if you know that it's a constant, that value goes away, okay? So differentiate. We get y3 dot plus 0 plus yb dot plus 0 equals 0, or y3 dot equals yb dot equals minus y3 dot. Okay, let's call this equation number 4. What else do we know? So we need to keep finding equations until we can solve for all of them, right? So ideally, you can say there are, how many unknowns there are? 1, 2, 3, 4, 5. We have 5 unknowns, we need 5 equations. We already have 1 equation here, 2 equations here. This third equation is actually a derivative of, it's derived from the first 2 equations, so this doesn't count. This is actually a third equation. We need 4 and 5. We need 2 more equations. So what else do we have? We can relate yb, y3, and y2, or y1. Y1 plus y3 is basically yb, right? So we differentiate, we get this. So basically this means that y3 dot equals yb dot minus y1 dot. Let's call this 5. Equate 4 and 5, or plug 5 in 4. We get yb dot equals minus yb dot minus y1 dot, which is minus yb dot plus y1 dot, or bringing the yb to this side, you have 2 yb dot equals y1 dot. Let's call this 6. So we have 6, which is a function of yb and y1. We have 3, which is a function of ya and y1. So 6 and 3, we can actually plug in 6 y1 dot for 6 in 3 to eliminate y1. So recall 3, which is ya dot plus 2 y1 dot equals 0, and then plug in 6 here. 6 in 3 gives us ya dot plus 2 yb dot equal to 0, and that's it. So ya dot equals minus 4 yb dot. This is a relationship between VA and VB, where we define VA as ya dot and VB as yb dot. Now, is VA given? So the velocity of B is asked, and the velocity of A is given to be 2 meters per second upward, okay, upward. So this mass is moving upward at 2 meters per second. If it is moving upward, what does it say about YA, which is defined to be downward? So YA dot is going to be negative 2 meters per second, because as the mass is moving upward, YA is going to be decreasing. So its rate of change of YA per unit time is going to be negative 2, right? So because A moves upward and YA defined downward, YA dot is basically minus 2 meters per second, which means that YB dot equals minus YA dot divided by minus 4, which is minus 2 by minus 4, which is 0.5 meters per second. So YB dot equals 0.5 meters per second. And because YB is defined downwards, this is moving down. Because it's a positive number and B is moving downwards, because YB defined as downward positive. Okay, so this is answer. And then we were asked about the acceleration of A given the acceleration of B. We can just differentiate this once more. So let's call this equation number, I suppose, 7 for acceleration. Differentiate 7. So you have YA double dot equals minus 4 YB double dot, and then we are given B accelerates downwards. I think it's given at 3 meters per second square. This basically means that YB double dot equals 3 meters per second square, which means that YA double dot equals minus 4 times 3 equals minus 12 meters per second square. Okay, so this would now be accelerating upward. So but this is the answer, by the way, and A accelerating upward at 12 meters per second square. Okay, so that's the problem. That's the solution to the problem. So what were the steps? You draw a big picture of the pulley, write down some key variables for the position of A, position of B. Just create some intermediate variables so that it makes your life convenient, perhaps, and then write expressions for the lengths of the various ropes while essentially ignoring any constants. Constants don't matter. The constants could be half circumferences of the pulley or things like this. So you can just ignore them or put them in as constants, and then when you differentiate, it goes away. So write those lengths of ropes down, and then try to relate the different intermediate variables that you have written down. And once you write some expressions for the intermediate variables, you essentially juggle the equations in a manner that you eliminate all the intermediate variables and you're just left with the variables that you really care about, which is the position of A and the position of B, or the velocity of A and the velocity of B, and and you get a relationship between them once you've eliminated everything else. And then you differentiate them once more to get an expression for the acceleration. A sort of essentially the same approach is you can say there are 5 variables, 1, 2, 3, 4, 5, and then if you write 5 equations in these 5 unknowns, you can set up sort of a matrix kind of problem, a matrix inverse problem to solve for the 5 unknowns in terms of the 5 equations. 5 unknowns given the 5 equations. Okay, that is implicitly what we did here without necessarily setting up a matrix and inverting it. Right. For these kinds of problems, it's if you have to do it by hand, it's easier to just do these kinds of substitutions to solve for these quantities directly rather than do a matrix inversion. But of course, if you have access to a calculator or a computer, which as we said, you're welcome to use in an exam, you can write down 5 equations in 5 unknowns and then do an inversion to get the solution. That's totally legal in this course. Okay, so let me stop there for this problem.